Hello, everyone. Welcome to the afternoon's tutorial on Android Haptics. We're really excited to be here with you today to introduce a new Haptics API, and we hope that this will allow everybody to create more rich and nuanced haptics on Android devices. So to begin with, let's first introduce the speakers. I'm going to start with Ahmad. Oh, here. Here. I'm going to come over this side.
Hello, everyone. My name is Ahmad Khalil. I am a software engineer at Google, part of the Android framework team, and I work on APIs that OEMs can use, and I help them integrate them into their devices. And I'm really excited to show you some of the stuff we've been working on. And next, my friend Nathan.
Hi, everyone. My name is Nathan Kolchak, and I'm also a software engineer at Google. I work on the Pixel Haptics system software. So I work on Pixel implementations of different haptics features.
I'm Hamte. I'm a research scientist at Google, and I work on both Android and Pixel haptics. My team also conducts user experience research and also psychophysical studies. Welcome. So this is the structure of our tutorial. Today we will kick it off. I will kick it off with some basics on human haptic perception, and then Ahmad will cover the Android API, and then Nathan will show you how Pixel implements those new APIs on Pixel devices. So part one, basics of human haptic perception. I'd like to start off by talking about the multiple entry points for APIs using this very oversimplified diagram. So when we create a haptic signal, you have a voltage waveform that's sent to the motor in the phone, and then out comes some sort of vibration. Usually that's characterized by acceleration. And we all know that depending on the frequency response of the motor, the acceleration you will achieve or the vibration you achieve will very much vary even if you have the same input waveform. And then the human hand touches the phone and it feels that vibration. And then we have perception. Again, that perception is modulated by, human sensitivity to vibration. And both of these, I'm not going to go through the details of these plots, but the fact that they're not flat means that the sensitivity or the gain of the motor is very much frequency dependent. So when you design a haptic signal, that's something that takes some work to think through. And one of the goals we want to achieve with the PWLE API, PWLE stands for Piecewise Linear Envelope. And what we want to achieve with that API is allow designers and developers to not think so much about how the motor works and how the human perception works, but think about how they want the vibration to feel like. Now, currently, Android API works in the voltage domain. So you have this thing called a one-shot where you can specify a duration, and then the motor will be turned on at the maximum amplitude for the duration you specify, like 10 milliseconds. So it'll be on for 10 milliseconds and off after 10 milliseconds. And the create waveform API allows you to also specify how strong the vibration can be. So this is on a scale of 0 to 255, 255 being the strongest. So you can say, give it two numbers. One is for how strong you want to be, and so 255, and then another number is for duration. So you can say 255 for 100 milliseconds, then 0 for 100 milliseconds, back to 255 for 100 milliseconds. So what happens is that the motor will be turned on full, and then it'll rest for another 100 milliseconds and on and off, right? So that's how you specify a pattern, but you can also use values below 255 to modulate how strong the vibration should feel like. We have 8 primitives also in Android where these are pre-baked waveforms on the phone that you can use. So I'm listing 5 of them, and they are also specified in the voltage frequency domain. So these are the quick rise, slow rise, quick fall, spin, and thud. The additional 3 primitives, these we call them the short primitives. These are click, tick, and low tick, are actually implemented based on the acceleration profile on Pixel phones. So that's why I put them, above acceleration. You will learn very quickly today that for the new PWLE API, the basic version, we try to allow designers to think about vibration in the perception domain. So what that means is that you think about how you want the strength of the vibration to move up and down. You think about how you want the sharpness of a vibration to move up and down. And this is all specified in a normalized parameter space. So you just change a number from 0 to 1, and you don't have to worry too much about how the human perception works and how the motor works. And Android does all the work for you. But for those of us who really want to have better control of everything, Android also has an advanced version. So in this version, you can say, I want the vibration to be at exactly like 80 hertz. And you can do that as well. Okay. I'm going to cover 3 concepts that might be useful to understand the new API. I'm going to start with detection threshold. So detection threshold is the smallest displacement or the lowest acceleration that can be reliably detected. And that's important because before you create any vibration, you want to make sure that people can actually feel it, right? And then there is a threshold below which that people can't feel any vibration, and these are just noise. So that's important to know. And the one thing to emphasize again is that detection threshold is highly frequency dependent. So on this plot, the detection threshold is the bottom curve. Right. This one. So that's labeled human detection threshold. And you also see this label called the 0 dB sensation level. So that means this is the lowest intensity you can deliver, and that's marked as 0. And the way we think about perceived intensity, as I have on the slide, is that perceived intensity according to psychophysical results is that they grow with the log of signal amplitude. So to make things easier, because we all like to think about things in linear space, you can see the ordinate of this plot is in dB scale. So we can convert everything to the log of amplitude. So here I have acceleration in dB relative to 1G peak, and I plot it on log scale. Then we can talk about the sensation level of signals. And we specify intensity in terms of how many dB above detection threshold a signal is. So all these lines that are in color above the bottom line, they're all parallel with the detection threshold curves. And right now they're spaced 10 dB each. And then, so right away, you know that if you have a vibration that's 1G, which will be this horizontal line starting from 0, right? Depending on what frequency it is, it may feel not equally strong to the human hand, right? Because you have to look at how much this 0 dB line is above the bottom line, and that's how you specify intensity. So what does sensation level mean, right? Is 20 dB strong enough? Is 40 dB strong enough? We know that 0 dB is the minimum, but why do I stop at 50 dB sensation level? What about 100 dB sensation level, right? So we have this little diagram, basically shows that between 0 and then 10 dB sensation level, which is the bottom 2 blue lines, the signal is perceivable, but it takes effort to feel it. So in other words, if you were in a soundproof booth, you have nothing better to do but to attend to your little finger that's, trying to detect whether there's a vibration. You can feel a vibration. But if you're holding a phone, you're moving around and something, the signal between 0 and 10 dB is really too weak to be reliably felt all the time. So in the PWLE API, we actually set the threshold at 10 dB SL to be, the minimum level that you should deliver vibration. And then from 10 to 30 dB sensation level, this is a comfortable range. That means you can clearly feel the vibration. They're not too strong. And if you're, holding the phone, you should be able to appreciate the vibration. They're noticeable and all that. Now, 30 to 50 dB, some people already will start to complain it's too strong, but most people still be okay with it. But above 50 dB is where we cut off because the vibration can be too strong that it just almost seems painful, right? The example is like if you're using a jackhammer, after a while, your finger just becomes numb. So that's why the line stops at 50 dB sensation level. And then lastly, I want to talk about the ideal operating range of actuators. So now it should make sense that, if you have an actuator, if you want it to be really, really capable, now you have a range of acceleration frequency space that you should target for. And that space should be between this light blue line that's marked 10 dB SL to the black line on top that's labeled 50 dB SL. So anything below that light blue line cannot be felt. But if you can do things above 50 dB SL, you actually want to limit it because people will not like it, right? So I'll try to show it with my hand. So basically, you want the space here between these two lines all the way up. And that's where the more of that area that you can cover with your actuator's output, the more sensations you can create for haptic signals. All right. With that, I'm going to hand it over to Ahmad to talk about the Android Haptics APIs.
Thank you, Hong. I think Hong did a great job introducing a lot of the concepts I'm about to talk about. So I'll be talking a bit about the Android Haptics API, and specifically, I'm going to be introducing the PWDs that Hong mentioned, these new APIs. And I'm also going to be covering something called the frequency to acceleration map, which we like to which we have a nickname for called the foam. And at the end, I'll also be touching on a new API called the vibrator vendor APIs, which would be interesting, I think, for some OEMs to make use of. So I want to start by talking a bit about the current haptic toolkit that we have. And I think Hong did mention most of these. So we kind of have three different ways of creating APIs at the moment. One is the basic on-off controls with the timing, and you can set the timings and the amplitude just turn on and off. We have something called predefined effects. These are kind of the old primitives, but these are predefined, pre-created, and you could just use them as is. We also have a way to create audio haptic effects. This would be a way to create a synchronized vibration, which we do through OGG files. The third way to create APIs at the moment is to use primitives. Here I mentioned all 8 of these primitives. These are also pre-designed. They kind of they're intended to provide a consistent experience for everyone, but it also depends on whether or not the OEMs actually support these primitives. So what are the actual drawbacks of these? Well, the first thing is that the vibration hardware actually varies quite a bit between these Android devices, which makes it difficult for developers to create reliable haptic that kind of works consistently across all of the different devices out there for users. And And this is a big problem. Like, this is one of the biggest problems. I want to create a haptic effect, and I want to make sure that it runs kind of in the same perception, or if it's felt in the same way by all of my users. And right now, it doesn't work that well. So what are we trying to do for the future? Well, we're trying to move towards a wideband haptics, which would enable richer, more dynamic, and expressive haptics effects more than just simple buzzing. We also want to try and move towards a design once, play all, where developers can create or design these haptic effects once and consistently have a high quality vibration across the Android ecosystem. And lastly, we want to try and enable hardware agnostic effects. But to achieve this, we need a new way for developers to define these haptics and make sure that it's not tied to the capabilities of the vibrator and the hardware. That's why we are introducing the PWE vibrations in Android 16. PWEs, as Hong said, the piecewise linear envelopes. It's a new and expressive way to create these haptics by defining a vibration using amplitude and frequency over time. It allows us to create these really nice, precise, rich haptics that just kind of plays in the same way or are felt in the same way across different devices. Now, I'm sure all of you are asking, why is the text smaller on this slide? Yeah. And that's a good question. The only reason is because I needed some more space to show this GIF. But what this new API allows us to do is stuff like this, where we have a bouncing spring, and as it bounces and then goes up, you can feel the vibration, and it kind of fades away as it goes up. And the second, as you can see now, it goes higher and lower, lower, lower. You can kind of sense that this vibration gets weaker and weaker as it goes. Now, I appreciate that showing vibrations is very hard if you don't feel it, but this would show how the waveform would kind of look like. You can see that it starts strong, gets weaker as it goes, and this is something we can actually do with these new APIs, which we couldn't do before. So in what we did add in Android 16 is these two APIs, the basic envelope builder and the waveform envelope builder. The basic envelope builder is an accessible approach, which doesn't need a lot of haptic knowledge to get into and to use. The waveform envelope builder is a bit more advanced. You will need to have a bit of knowledge in haptics and the hardware behind that to be able to use, but it is available for everyone to try. So I'm going to go into some of the details of the basic envelope builder. As I said, it's an accessible approach. Doesn't require a lot of hardware knowledge, and you can define these using intensity and sharpness between the levels of 0 and 1. And so this is a familiar plot with Hong just talked about, which was great because she introduced a lot of these difficult concepts. But just as a reminder, SL is the sensation level, and we are introducing this new minimum threshold, which is a 10 dB SL. So what this means is these new APIs, or specifically the basic API, we won't allow, if an OEM or a device wants to support this, they will have to be able to provide vibrations that are above this minimum threshold, which is the 10 dB SL. So the reason we have this is we want to make sure that if you're creating an effect, people will actually feel it. We don't want to have cases where, I have this really cool effect, but I kind of don't feel it very well on this device compared to the other one. So I want to make sure that it is felt. The other thing about this minimum threshold is it also defines the frequency, the sharpness range on that device. I'll go a bit more into some of those details later on, but in short, when we set this minimum threshold, we look at the start point and the end point where it crosses the minimum threshold. The foam crosses this minimum threshold. And based on that, we can decide where the 0 sharpness starts and 1 sharpness ends. But I'll go into more details and I can show you exactly how that would look like. Something else that we also do in the basic API. So if you can look at the top right plot, this shows you what the vibration or what the control points would look like for you as a developer. So you would be setting values between 0 and 1 for the intensity and 0 and 1 for the sharpness. But this maps to what we have on the lower right. The reason is we use an exponential function to get to this point. So it's not so you don't really need to worry about how to do this. We kind of do this for you. Like the framework actually does all of this work. We have a way to convert these intensities into sensation levels and decibels and come up with the acceleration that we need. It is there just to show you how it ends up looking. But again, the reason behind the basic envelope builder is developers don't need to work with this. They could just use it as is and expect it to work every time. It does come with a bit of limitations. It does need the effect to start and end at a 0 intensity. Now the API does the work for the start of the vibration, but the end, we need the developer or designer to actually set it to 0. There's a reason behind that, which is related to if you have a repeating effect or you have something that's gonna run again, we kind of want to make sure that we don't have any gaps there. It may also not use the full range of the frequency. This is also based on what I mentioned before, which is related to the 10 dBSL. So yeah, as that's what I mentioned. The Android framework will automatically adjust the effects to kind of fit within the boundaries of the device. This is in the cases where the effect is too long and we need to kind of cut it. Like we will try to do it, but it's as much as possible. So it's worth keeping that in mind. So I've been talking a lot about this basic API. So how does it look? So it's as simple as this. It's just a builder, basically. You set an initial sharpness if you want. You don't have to. And then you just set control point after control point. And that's it. You just build it and you run it as if it's a regular vibration. For example, in this one, we are ramping up the intensity and sharpness from a low to a high level over 500 milliseconds. And then we ramped it down to 0 over 100 milliseconds. As I said, the initial sharpness is optional. If it's not set, it would just default to the value of the first point. So as the graph kind of shows you how this would look like, but it's a very simple API to work with, and you don't really need to worry about because you're using the 0.1, and the framework will make sure that this is within the boundaries of the device. So hopefully nothing can go wrong. Famous last words. So we've seen this this animation before. So how do we actually do that? Well, the code is actually quite simple, but this is it. We start from a sharpness of 0. We then go up to this new intensity and sharpness over 200 over 20 milliseconds, and then we just go back down. We drop the intensity back down to 0 over a fade out duration. Now, the only tricky part is figuring out that fade out duration. It really depends on how fast the spring hit the ground, and kind of calculate how high it's going to go, and that's how we get the fade out duration. We are working on we are working on publishing the code for this. It's not out there yet, but it's in progress. So you would be able to see this and see exactly all of the code to actually. Also, we're gonna be probably gonna demoing this after this talk, but you can also head to the Google booth and you can actually experience it on some of our devices. It's a lot cooler when you have a phone in your hand than just seeing it as an animation. I promise you. So the second API, which we call the Waveform Envelope Builder, I might sometimes call it the Advanced API, but it's the same thing. So it kind of needs more knowledge in the hardware. It's an advanced approach to create these effects, and you create them by defining amplitude, and which is between 0 and 1, and actual frequencies. So you just set the actual hertz value. We don't really enforce limits, but this also means that it's on the developers' a responsibility to make sure that the frequencies are within the capabilities of the device. If an effect is outside of these capabilities, we simply don't run anything. So we have it there, we can use it, but you just need to make sure that it's going to work every time. So it looks a lot like the basic API. This is an example where we're defining a 400 millisecond vibration. It begins at 60 hertz for 50 milliseconds, ramp up to 120 over 100 milliseconds, stays there for about 200 milliseconds, and then returns to 60 hertz over 50 milliseconds while the amplitude drops to 0. Here I kind of omitted the frequency, initial frequency, and because of that, it just starts at the first point. As you can see, it's going to be 60 hertz. So what would this allow us to do? Well, it allows us to do quite a bit of work. And here, this is my best attempt at creating a rocket ship. I know the UI is amazing, but anyways, the way we do this, it kind of creates this buzzing effect as the rocket is going up, and it kind of gets stronger and stronger, more intense, and then as soon as it kind of gets out of orbit, it gets loose. So what we did here is we got the lowest frequency where we can get a specific output acceleration. I think it's about 0.1, and then we just needed to calculate how much ramp up duration we want and how much ramp down we want, and we just went from 0 or from whatever the first point that we can get this 0.1 amplitude, go up to the resonant frequency, makes it quite strong vibration, and then we just let it out. And again, when you have it on your phone, on your device, and you feel it, you can feel like, oh, it's as if it just kind of flinged off. So please do pass by the booth as well to experience this and watch the amazing animation. So I mentioned the frequency to acceleration map previously, and the phone. And the reason this is important is because it defines the frequency to maximum achievable output acceleration curve. And this is crucial, especially when using the advanced API, because this allows you to know what is the frequency range that this device can actually provide. So it helps ensure the effects uses the frequency within the device capabilities, and all of this can be provided by the vibrator frequency profile API. So you can kind of see here in this graph, like where, for example, at 50 hertz, you can see that the maximum achievable is quite low compared to when you're closer to 120, 130, it's quite high. So you need to make sure that you have this in mind, and you make sure that, okay, my effect needs to work within this range, and to provide the perception or the feeling that you actually want in your effect, in your vibration effect. So here is where I was talking about previously about the sharpness range. So there's the shaded area. This is the area of the sharpness range. It's where the minimum threshold, the 10 dBSL, cuts the phone curve first time and then cuts it the second time. And this is how you would know, okay, my basic API is going to provide me a vibration within this range. Now, there are cases where it won't cut again. So you have this second thing, but just keep on going. And in that case, you just have the rest of the entire frequency range to work with. So it is important to keep this in mind when working with the advanced API. So this is kind of shifting towards another API, which is the vibrator vendor API. So we're introducing this new system API to allow access to the vibrator hardware. It will allow vendors to prototype and experiment without relying on new APIs from us. They can just experiment with it. The vendor privileged apps will send opaque vibration effects to the vibrator HAL directly, and we call these effects vendor effects. So as I said, these vendor effects are also system APIs. So the hardware-specific opaque effects are sent directly to the vibrator, and then the framework metadata will be sent separately, like the user settings, intensity values, and so on. And also like the adaptive haptic scaling, for example. So those will be sent separately. The vendor, we also have the vendor vibration session, which is also a system API for vibration playback control. The vibration session is initiated with a fixed vibration attribute. Async operations, it's an async operation that will return the session once it's successfully started. The vibration uses prioritized session vibration against the system vibration. Once started, the framework will grant the session sole control over the vibrator entirely. And we also, so we have these session callbacks as well. So the session can be immediately interrupted by the vendor client. It can be abrupt. It can be aborted by the vibrator hardware or the Android framework. And the session closer is also asynchronous with a final callback once it's stopped. Lastly, the session vibration effects are forwarded to the vibrator straight away. So the vibration effects can be sent through the session while it's active. Effects are forwarded to the hardware immediately, as I mentioned before, and it gives the flexibility for vendors to decide how to handle multiple effects like queuing, real-time updates, and mixing. And with that, I will allow Nathan to take over. Thank you very much.
All right. Thank you, Amin. I will be talking a bit about how we implemented the system software portion of the Pixel, or system software portion of the PWE APIs to support the Android framework on Pixel phones. So to support the new Android level APIs, you have to implement a number of new methods in the vibrator HAL. So if you're not familiar, the iVibrator service is a service that runs on Android phones that provides a hardware abstraction layer for the Android framework to call and generate effects. So for example, this iVibrator composed PWE v2 is the underlying API that the framework would call whenever it's playing any envelope effect. There's a number of other effects that expose the hardware capabilities. For example, so you have to expose some other device information for playing back custom PWE effects. Part of this includes characterization of the device's hardware. So this is the responsibility of the OEM to characterize what their hardware can do safely. And there are a few requirements for actually playing back PWE effects. So your hardware has to support creating new effects at runtime and playing them back through the amplifier. You have to be able to generate a PWE effects either through direct dedicated support for PWE effects or the ability to play back arbitrary waveforms. And then also you have to be able to generate and expose an actuator response profile. So all of the APIs that Amma talked about rely on this device characterization where there's the frequency to output acceleration map that is exposed by the HAL service. And then as part of supporting the PWE APIs, you need to implement a method for actually generating that on the device and exposing that. So on Pixel phones, we currently use Cirrus amplifiers, and we implement the PWE APIs using a feature that the Cirrus amplifiers support called the open wavetable, which allows you to upload new effect definitions at runtime over I2C. So currently we're using this proprietary hardware APIs to implement this, but it's not strictly necessary. And then we also use some proprietary hardware support that limits the voltage level around the resonant frequency to prevent actuator excursion. So if you think back to the foams that the frequency to output acceleration maps that Ahmed showed in his slides, you see like that cutoff around the resonant frequency. And this is a sort of extract version of what a foam would actually look like where we have this safety limitation around the resonant frequency that prevents actuator excursion. So device safety is the responsibility of the OEM to implement. And the framework expects that any effect that the system service says it can generate, it can play safely. And then on Pixel phones, we also have factory calibration that we can use to generate the frequency to output acceleration map so it's more accurate for each device. So this improves the response range and the scaling accuracy when we are translating effects from the perception parameters into acceleration parameters. So this is an example of a frequency to output acceleration map on the Pixel phone. So currently Pixel phones use an open loop drive mode when they're generating PWE effects. So the underlying acceleration model we use maps voltage and frequency to acceleration. So we then map the amplitude range using this acceleration model to the voltage range. So for each frequency, we know that the foam expose. So we use this acceleration model to generate a frequency to output acceleration map that we expose through some of the new APIs added to the HAL service. So this is one example of such a frequency to output acceleration map. So you can see on the left, this is the voltage range that we have available as defined by the voltage limitation curve that we use for device safety. And then on the right, we have the acceleration curve that would actually be exposed by the HAL to the vibrator framework that is calculated using this voltage limitation curve and our acceleration model on Pixel phones. And because we have this voltage limitation that we map the incoming amplitude to, we know that our Pixel phones will never try and play an unsafe vibration effect because 1.0 maps to the maximum safe voltage value. So this gives us a couple of quality improvements aside from the actuator safety. This also helps prevent like amplitude distortion of an effect as it's being played. So because we're never going to try and generate an effect that would be limited by the hardware safety features, the effects that we play will also generate accurately to the effect definition. So this prevents amplitude distortion that would be caused by our hardware output clamping the voltage down and playing a weaker effect than you might expect, or an effect that has a different amplitude envelope than you'd expect because it passes through a portion of the voltage limitation curve where the maximum voltage is lower than the previous point would be. So on Pixel phones, we use the factory calibration data. This includes the device's resonant frequency and the Q factor, as well as some other things like the DC resistance. So this is really important to the output quality, particularly near the resonant frequency, because as you can see, the actuator output is very sensitive to voltage changes near the resonant frequency. So as an example, this is some plots we generated while we were doing investigation to generating the frequency to output acceleration map. And on the left, you see a maximum steady state voltage curve versus the frequency. And as you can see, this is a calibrated curve because the resonant frequency is aligned with the minimum voltage, or the minimum maximum voltage, I guess. And then on the right, we have the map to acceleration map. And you can see that this is not a calibrated map because the resonant frequency does not align with the maximum amplitude. So this map would be using, for example, a device's nominal values. So the expected resonant frequency would be centered around 130 hertz, but this device's actual resonant frequency is 131.16 hertz. I'm not sure if you can read that. And you can see that even this tiny, like 1.1 hertz change really throws off the frequency to output acceleration map. And you can see, so right here is where it crosses, and here's what the expected maximum amplitude thing is that just this 1 hertz change shifts the maximum amplitude, which puts the half flags down by 0.25 Gs. So that's like essentially almost a 1/6 reduction in effect strength, just from a 1 hertz difference from the nominal resonant frequency to the actual resonant frequency. So this, I think, shows the importance of using the calibrated device values. Similarly, the Q calibration is also, Q factor calibration is important because, like the resonant frequency, small changes will throw off the bandwidth around the resonant frequency significantly. And this can also cause amplitude distortion if you expect a wider, if you expect like a wider map than you actually have. Because, for instance, if the Q value is wrong and this is significantly narrower on your actual device than you are reporting to the Android flavor, then you're going to also have this effect distortion as values around here came below the expected acceleration value by the hardware safety features or by the HAL limiting the voltage output. So then on Pixel phones, we also have some automatic testing that we do. So we have some automatic waveform analysis tests that are executed regularly. And these try to quantify the accuracy of the foam that we're exposing from the system service. And this is so that we can detect regressions in quality from new builds if we, say, change how we're calculating the foam or enable new hardware features. We can detect if there's a decrease in output accuracy. We also use this as a sort of minimum quality gate for new phones. So whenever we're trying to add PWV support to a new Pixel phone, we can use these tests to ensure that it's at least as accurate as the existing phones, so that any effects that you had designed for other Pixel phones will feel similar on the new Pixel phones that support it. Sorry. Thanks. It's hot. There. And then we also have additionally integration tests that check for regressions in stability and latency. So these are end-to-end tests that check for increases in the latency between, say, touching the screen and the haptic effects starting, or regressions in stability of the haptic effects of the system. So the next section, we're going to talk about another new feature that we is planned for Pixel phones that we're currently developing. So right now we're investigating some options for exposing real-time parameter control, sort of an expansion to the PWE API that we've described so far. So this, we're hoping to enable more real-time UX interactions and potentially gaming. So the primary focus of the real-time API expansion is enabling real-time parameter control for PWE effects. So the controls we're looking at are amplitude scaling, which you can see on the left. So if you imagine this is just like a phase effect playing at the resonant frequency, and the user is dragging a slider around that is tied directly to the amplitude scaling factor that's modulating your real time, you can see sort of how that would affect the output waveform. And then we're also looking into frequency modulations. So that's on the right. You can imagine the same base effect, but instead of modulating the amplitude in real time, we're changing the frequency in real time. So you can see that the actual output, the output waveform has like a smoothly ramping frequency offset. And so we're looking into a few different options for implementing these APIs and interfaces for how we can expose them. So this includes things like the vendor APIs that Ahmed discussed previously, as well as public APIs or other pixel-only implementations. So currently, the engineering build that we have for real-time haptics adds support for two types of effects that have some distinct behavior, both by themselves and how they interact with other effects. So the first new effect category are continuous effects. And these are indefinitely long effects that are defined periodically. So you can think you would use these for, say, UX interaction where at the start you don't know how long it's going to take. So this could be something like if you have a haptic that's tied directly to some sort of slider or like modifiable UX element, or things that rely on hardware feedback to know it's ended. So things like unlocking the phone using the fingerprint sensor. You don't know exactly how long that's going to take, but if you want to synchronize, say, the animation with haptic serving output, then you could use something like a continuous effect. And so the continuous effects are defined periodically. So the effect definition is essentially one period of the effect. So this includes standard PWE effects, which are just like a sinusoid waveform, and also more complex repeating envelopes. So it doesn't just have to be like a flat waveform as the base effect. You can define something that's more complex. And because the effect is defined as a single waveform period, and PWE effects must start and end at zero amplitude, the starting and ending behavior is defined separately from the effect definition. So this is sort of part of the API instead of part of the effect definition. The second type of effects that we're looking at are transient effects. So these behave more like the typical Android effects that we have now, where they do have a definite duration, and the effect definition includes the entire effect. With these APIs, like the continuous effects, we also have the ability to modulate the amplitude and frequency of transient effects, assuming they support that. So for all of these, you would be able to, say, scale up the amplitude or add a frequency offset modifier in real time based on input from the user or different like system events like a game. So we can combine these new effect types and the features that they support in some interesting ways that lets us create some haptics behavior that was either not possible or difficult to produce consistently before. So, for example, this is an example of a transient effect interacting with a continuous effect, where we have this thing we're calling interrupting, where the transient effect, say for instance a click effect in this case, will interrupt a continuous effect by using amplitude ramps before and after, so that the output waveform, the output voltage will drop to 0 before the new effect tries to play after the effect plays. So this lets us create these more consistent, complex interactions between haptic effects that were difficult to do with existing APIs. So that is all that I had for the pixel section. And then I think, thanks.